So in this video, we'll be looking at the hydration of carbonyls. So this is going to be a great way to add hydroxyl groups to a carbonyl, right? If we want to look at the general mechanism, or the general scheme of this reaction rather, we can have a carbonyl here, right? We have our two R groups and a double bond to an oxygen. This is going to react with water. Now, you should know that one, this is a reversible reaction, and we can actually do it in either an acidic environment or a basic environment. Both of these would work and give us the same product, where we have again these two R groups, and now in place of that carbonyl we have two hydroxyl. So this is what we call a hydrate. So we form a hydrate. The mechanism is going to vary based on if it's occurring in an acidic environment or a basic environment, but this product here is still going to remain the same. So let's begin with a mechanism for this reaction under acidic conditions. So under acidic conditions. So if we are under acidic conditions, right, the general way we can write this is first just going to be like this. Again, kind of what we just did right now, right? We have a carbonyl reacting with water. We have to make sure to write these reversible arrows, or equilibrium arrows, and this is happening in acid. We're going to then generate a hydrate, like so. Now, what you should know is that the acidic conditions are going to be more favorable for this reaction than the basic, than a basic environment. These are the more common conditions for this type of reaction. Now, this reaction is really going to happen in 3 steps. The first thing we're going to do is we're going to have a protonation. We're going to have a protonation. We're then going to follow this with an addition. And finally, there's going to be a deprotonation. So really, if you want to think about it, this protonation, what it's going to do is it's going to make that carbonyl more reactive. It's going to activate it for the addition step. So when you add this proton to our carbonyl, it's going to be very reactive. It's going to want to react with, effectively our source of hydroxyls here, right, water. And then we are able to do that addition reaction. And once the addition is done, we're going to deprotonate. We're going to take that proton off. So we're kind of turning it on and off, almost like a switch, right? This turns it on, so then we can go with the reaction, and when we're done with the addition, we turn it off by deprotonating. So let's see how that works. So let's start off with our carbonyl. So like I said, we're going to have a protonation. What is the source of the proton? Well, it's going to be the acid, right? Our H3O+. This is why we're doing this in acidic conditions. So we'll get a lone pair on our oxygen here to grab onto a proton, pushing these electrons off. So this is that protonation. And this is what's going to generate what is called an oxocarbenium ion. Oxocarbenium ion. So this is going to then have a plus over here. So this is the oxocarbenium. Now the oxocarbenium, like I said, is active for addition. So what we're going to then have is we'll have a water molecule go in for the addition here. So we'll go have it attack this carbon, which pushes these lone pairs of our oxygen, lone pairs onto our oxygen here. So this is that addition step, giving us something like this, where we have the OH as well as the OH2. Remember, there's a plus. So then what we're going to do is that deprotonation. So what we're deprotonating now is going to be this group here. So we'll take one of our water molecules, because remember, this is occurring in solution. We don't have just one. We're going to have more than a couple water molecules in solution, so we can use one of those lone pairs to grab onto this hydrogen, pushing off the electrons there. This is the deprotonation, giving us our final product, that hydrate. So this is going to be the reaction again, and then we still have our acid. But this is going to be the mechanism for the forward reaction under acidic conditions. Now, what about the reverse reaction? Remember, we saw that these is a reversible reaction. We draw our equilibrium arrows here. So what does the reverse mechanism look like? Well, for the reverse reaction, we're going to have, again, right, what we just generated, we have our hydrate. And what it's going to do is the first step here is going to be a protonation, right? So we'll protonate using acid as before. So what will happen is we'll use a lone pair and oxygen, grabs the hydrogen, pushes these electrons off, giving us this guy over here. Now, we're going to have now an elimination reaction, right? This water here is going to be a good leaving group. So what will happen is we have a lone pair here collapse to generate a double bond, which then kicks the water off. So this is an elimination. So we eliminate that water and generate, again, the oxocarbenium now, right? So we have a double bond, oxygen, and then a hydrogen. There's a plus charge here. And finally, we'll have a deprotonation where we get rid of this hydrogen. So we'll use a water. We'll use a water molecule, which uses its lone pairs to grab the hydrogen, push these electrons onto our oxygen, and now we have generated that carbonyl once again. So this, again, plus H3 plus, is the mechanism for the reverse reaction of our carbonyl hydration under acidic conditions. Now, let's now take a look at this reaction in a basic environment, right? So if we want to look at it in the basic conditions, let's see how this is going to play out. So for the basic reaction, what we're going to have is, again, the carbonyl, right? That's going to stay the same. We'll have the carbonyl, we'll have the water. But remember, this is under basic conditions, so what we can have is some sort of base. We can say NaOH, for example, which is going to be a source of hydroxyl groups. Again, we have a basic environment, and the end product, though, will be the same. We'll still be forming a hydrate. So, what is the mechanism? We'll start off here with an addition reaction, right? So we'll have our carbonyl. And so we'll use the hydroxyl group that we get from our OH. Remember, this NaOH can dissociate when in water into this sodium ion and hydroxyl group. So what we'll see happening is we'll use the lone pairs here to grab on, right, addition reaction to the carbon, to the carbon, push off these electrons up here. So this is an addition, which gives us R, so our two R's. We'll have now the OH, and we'll have an oxygen here, right, with a minus charge because there are three lone pairs. So now what we're going to have is a protonation. So we're going to try to protonate this oxygen here. So we'll use our water to be our source of protons. And so the oxygen is going to grab this hydrogen, push off the electrons onto this oxygen here. So this is that protonation event that will give us our product, our hydrate. So this, and then again, plus OH minus. This is the mechanism for the forward reaction for our carbonyl hydration in basic conditions. Now, the reverse reaction, if you want actually to try to do that on your own, you want to pause the video and try to see how we can reform our carbonyl from a hydrate under basic conditions, feel free to do so. But we'll go through it together right here anyway. So we have our hydrate, right? The R groups, the two hydroxyls. So what we'll start by doing here is going to be deprotonation. So we'll have a deprotonation event. So we'll use this hydroxyl, right? Here, let's do this. Just for the sake of clarity, let's draw that bond out a bit more explicitly so we can have O bonded to an H. So we'll have the lone pairs on this oxygen, grab the hydrogen, push those electrons onto the oxygen here. This is deprotonation. That will give us this. Where then, again, we've generated water now, right, as well, in this way. And we'll then do an elimination reaction where we're able to use the lone pair here to push down. We'll use the lone pair here to collapse and then kick off this OH. So this is an elimination that will generate our carbonyl. And again, now we have still our OH minus in solution. So this is going to be the reverse reaction for carbonyl hydration in a basic environment. So hopefully that's making sense. These reactions, the mechanisms here look pretty straightforward. There isn't too much going on, so hopefully it wasn't too difficult. If this video was helpful, please show your support by liking and subscribing. Leave in the comments any questions you may have, as well as suggestions for future videos, and I will see you in the next one.